The standard normal distribution. So let's say we have a problem, the SAT versus the ACT, because this is a common example for students. We have Joe who took the SAT, he scored 620 on the math, and the distribution of the math scores is normal with a mean of 520 and a standard deviation of 120. John took the ACT math test and scored a 25. ACT math scores are also normal with a mean of 21.2 and a standard deviation of 4.8. So here's the problem. Both are applying for the same scholarship, and the scholarship committee has determined that the two students are alike in every way except for their standardized test scores. The committee wants to give the scholarship to the student that performed better on the test. Since both boys took two different tests, how can the committee decide who's going to receive the scholarship? So in order to figure this out, we have to talk about standardized normal distribution. Okay, next. Sorry. Oops. Okay, so we have been dealing or working with the normal curve. When we've been working with the normal curve, we've gone through and we've been labeling where our mean is. We've been labeling it mu. We label this mu plus 1 standard deviation, mu plus 2 standard deviations, and mu plus 3 standard deviations. We've then also been doing it in the opposite direction, but using subtraction. So when we're doing this, oops, sorry, we have our normal curve, and this works for any normal distribution. But now we can't really do the same thing as we have been, especially when we want to compare data that has different sets of numbers. Because if we put these on the same number line, they're not going to work. So instead what we do is we standardize that normal curve. And instead of having all of these numbers going across as your label, we're going to change those numbers to these 7 numbers, where the mean is going to become 0. And 1 standard deviation above is just going to become the number 1. 2 standard is 2. 3 is 3. And then to the left, going below the mean, is also going to be -1, -2, and -3. You'll see here that I've labeled the x-axis as z. We start calling these scores z-scores because we're standardizing them. So why do we need to change the labeling of the curves? If we took our information from before, we know that, oh, what happened? We see that we could take these and we could label our set of information where we could have this as Joe's SAT scores, and we would have that his mean is 520, and we go up by 120 for each standard score, so 760 and 880, and here we would have 400, 280, and 160, and we could take John's ACT scores and we could label his as 25, 29.8, 34.6, and 39.4, and then going left, 20.2, 15.4, and 10.6. Oops, didn't kind of merge together there. But what we can do is we can, if we look at these two sets of data on the curves, the numbers underneath are so off. If we were to put these on one number line, we would end up having one curve way down here and another curve farther away over here. So it'd be very hard for us to tell the difference. So we need to change the labeling of curves in order to compare sets of data that are different. So to compare data that are not the same. They're not the same label. This is the SAT scores, this is the ACT scores. They're totally different tests. So if you were doing something like heights of kids, you would have heights of 18-year-olds versus heights of 10-year-olds, and those wouldn't be the same, so you would have to do the standardizing of the data. You're comparing data that is similar, but they're not exactly the same. So standardizing scores. Basically, when you're standardizing scores, you are finding what we call the z-score. Standardizing score makes them so that everything is the same. And in order to find the z-score, you have to do the mean, excuse me, not the mean. You have to do, oops, delete. You have to do the data value minus the mean over the standard deviation. So you're going to have to know at least 3 different pieces of information in order to find the first. We do a short notation where we just do z for z-score, x for the value, minus mu for mean, over sigma for standard deviation. It's important that you have this formula written down because it's going to be used in throughout the rest of this lesson. So let's standardize our SAT scores and see who did better. So Joe, we know, took the SAT and scored 620. So his 620 value equals X. That's his data value. The distribution of the SAT scores is normal with a mean of 520. So we have a mu of 520 and a standard deviation of 120. Okay, so if we're going to find Joe's z-score, we're going to use the formula z equals x minus mu over standard deviation. Remember, you need to start remembering that formula. For now, you can keep referring back to it. So now just substitute in for your three variables that you know. So we know z, we don't know z, so z is z, equals x, we know is 620, minus 520 over 120. Do your simplification, so 620 minus 520 is 100 over 120. Now use the calculator and actually do the division of 100 divided by 120. And you're going to want to start rounding to the nearest hundredths place, so 2 decimals. So our z would equal 0.83 for Joe. So now let's do the same thing for John. So John's info, we have his score was 25, so x equals 25. The mean of the ACTs is 21.2, and the standard deviation is 4.8. You're not always going to have numbers that are whole numbers. Sometimes you may get decimals. So now do your substitution. So z equals 25 minus 21.2 over 4.8. Do your subtraction of 25 minus 21.2. So you end up here with z equals 3.8 over 4.8, and do your division, and you're going to end up getting that his z-score is 0.791, so his z-score is 0.79. So here we have their two z-scores. Well, the person with the higher z-score actually did better on the test. So who did better? Good. Joe actually did better on his test because he has a z-score of 0.83. Okay, John's z-score is only 0.79. Granted, they're very close. Joe clearly did better on his test. So who's going to get the scholarship? Joe will. Okay, so sometimes you're not always going to be asking just to find the z-score. You may have to find other parts. So the trick is to still remember that z-score formula where z equals x minus mu over the standard deviation. Okay, and you go through and you see what you have in your problem. So a normal distribution with a mean of 50, so mean equals 50, and a z-score of 2.3 and a value of 60, so x equals 60. So you know 3 of your variables, and we're trying to find standard deviation. So just substitute in. So you have 2.3 equals your x, which is 60, minus 50 over the standard deviation, which we don't know. In order to simplify the numerator, 2.3 equals 10 over the standard deviation. What do you do to solve? Cross multiply, so essentially you have 2.3 times the standard deviation equals 10. Do your division, and you end up getting your standard deviation equals 4.35. And again, start using 2 decimal places for when you're doing your calculations. Okay. Sometimes you may be given different information where you have a mean of 35, mu equals 35, a standard score of 1.5, and a standard deviation of negative 1.6. That's a typo. Okay, this is supposed to be negative 1.5, and this is supposed to be positive 1.6. So please change those on your paper now. I apologize. So do the substitution. You have negative 1.5. It's okay to get a negative z-score. That just means that you're going to have numbers less than the mean. Okay, we're trying to find the value or find x, so that's our x, minus 35 over 1.6. So in order to solve, cross multiply. So when you cross multiply, you end up with negative 1.5 times 1.6. So you end up with negative 2.4 equals x minus 35. Add 35 to both sides. So you end up getting your x equals 32.6. Okay. So You can find standard deviation if you know the mean, the z-score, and the value. You can find the value if you know the mean, the standard score, and the standard deviation. And you can find the z-score if you know the mean, the value, and the standard deviation. Okay, just a few things to make sure you know when you're looking at the curve. Here, if you get a negative standard score or a negative z-score, you end up having a number that's less than the mean. That's going to come into play and be important next time. Okay, if you have a positive z-score, that means your number is above the mean, that the person or the score or whatever it is that you're gathering data on did better than average. Okay, so you can get a z equal to a negative number. Okay, so that's basically standardized scores in a nutshell. So we're going to be doing more with these throughout, so just make sure you don't lose these notes pages with you.